Okay, here's points back step 2. Let's do a similar example to the first one. So we've got the velocity of a particle is given by this function, and they want the acceleration of that particle at time 7. Okay? So limit, derivative, or antiderivative, you need the derivative. And if they're asking for the derivative at a point, you should use your calculator, all right, because this is a calculator section. I'm going to go to my home screen. And so we're going to use Math 8, all right? Because really, like, you could find the derivative by hand and then plug in 7, but this is so much faster, and you've really got to save time where you can. So you go Math, and then you hit the number 8, and then this pops up. So we plug an x in there because that's the independent variable. That's the input variable. And then in here I plug the function. I'm going to go alpha y equals, if you have a nice calculator, it'll just set it up like that. And then sine of 3 x squared over x minus 9. And then over here you put, this means, this here means evaluated at, and then you plug the number in. So evaluated at 7, yes, and there it is. Okay, so the acceleration at time 7 is approximately 16.4989. Okay, so moving on. So number 2, here is a similar example. So I'm giving you that the integral from 1 to 2 of f of x is 5, and the integral from 2 to 9 of f of x is 3, and with that information we want to find the integral from 1 to 9 of 3 f of x minus 7. Okay, so I recommend that you break this up. Yes, okay, so this is 1 to 9, 3 f of x dx minus 1 to 9 of 7 dx. Okay. And right here, okay, so now I guess I'll pull out the 3. Yeah, maybe, okay, I could pull out the 3 like that. Okay, and now I don't know the integral from 1 to 9 of f of x, but I know the integral from 1 to 2 and the integral from 2 to 9. And if you take the interval 1 to 2 and you put it next to the interval 2 to 9, you get the interval 1 to 9. So this is 3 times, I'm going to do a bracket here, the integral from 1 to 2 of f of x plus the integral from 2 to 9 of f of x, close bracket, minus the integral from 1 to 9 of 7 dx. Okay, so this is 3. And now I know that this one is 5. And I know that this one is 3. Minus, now you could use the fundamental theorem, but this is a calculator section, so I'm just going to go math 9. Okay, so math 9, and then from 1 to 9. Yeah, anything you could do to save yourself time is great. So 56 minus 56. So this is 3 times 8 minus 56 equals, so 3 times 8 is 24. 24 minus 56 is negative 32. So that would be the answer. Okay, now down here, we're going to let f of t equal some function of time. Okay, so time is the input. And we're going to interpret f prime of 10. All right? Well, a derivative is a rate of change. So, yeah, so this is a rate. Okay, so it is this. It is the rate at which F is changing at the moment t equals 10. And this is very important, at the moment. So when you are trying to do work to correct this problem, you are looking for the choice that says that, it's the rate at which the thing is changing at a certain moment. So you're looking for the language that indicates change at a certain moment and not change over an interval. Change over an interval would be average rate of change. And the derivative is instantaneous rate of change, which means at a certain moment. Okay, so a similar example to number 4. So I'm going to tell you that at t equals 0, we've got 100 gallons of water in a tank, okay? And that water is pouring into the tank at a rate of cosine radical x. And we're going to find the amount of water after 3 minutes. Okay, so you ask yourself limit derivative, antiderivative, and really, guys, okay, I guess maybe antiderivative is the closest of those things. And really, we want the net change in water, okay? The net change in water. Okay, so that's how much the water has changed within a certain interval. And guys, if you look at AP Calculus exam topics to look for, part 1, all the way down here, there's something called the net change theorem. And here it is. The net change of F over an interval is given by this. So if you want the change of something over an interval, you take the integral of its rate of change. All right? So that's what I'm going to use. So I need to go, so find the amount of water after 3 minutes. So we start with 100 gallons, and then we're going to add the net change. Okay, and then in here is going to go cosine of radical x dx. Okay, so this is the net change right there. Okay, it's the integral of the derivative. And yes, now I said antiderivative because if this was a non-calculator section, we totally would have to take the antiderivative doing the fundamental theorem of calculus, but we could just use math 9. So this is 100 plus math 9 from 0 to 3, and then cosine of radical x. Okay, so 101, so it only changed like 1.098045 gallons. So this is the amount of water is approximately 101.098. I'll say 05. I used 5 decimal places. Okay. Now this one. So if f prime of x equals 10, sine of 10x, how many points of inflection does the original f have in this interval? Okay, and whenever you're dealing with like points of inflection or extrema, maxes or mins, you ask yourself limit derivative or antiderivative. This would be the derivative. But again, similar to the last example, if we were on, if this was a non-calculator section, we for sure would need to actually find the derivative of this because you need the second derivative for points of inflection. However, we could just use our calculator, and I'm going to show you how in a moment. Okay, so you need to know about Susan's table, all of this stuff. So you look at, all right, so we're looking for points of inflection, all right? So in Susan's table, you know, we're looking for points of inflection. So we're either looking for extrema of f prime or sign changes on f double prime. Well, since we're given f prime and we have a calculator, if I were you, I would look for the extrema of f prime. Okay, and shout out to Emily. I saw you doing this, and this is why I'm doing it this way. I was going to suggest you take the second derivative and then graph that, but that's way more time. And so, yeah, good job. Okay, so I'm going to graph this function on that interval, and I'm looking for extrema. So I'm going to go y equals, and I already did it. Okay, I graphed that. And then for the window, I want the x min to be this, so I go negative pi over 8. And then I want the x max to be pi over 8. And then I graph this, okay, and it looks something like that. And this is the graph of f prime. Let me go back to Susan's table. So this is the graph of f prime, and wherever it has extrema, those points correspond to points of inflection on f. So I just have extrema at two places. There's a max, or no, that's a min, that's a max. So I've only got two. So maybe let's draw this picture. Okay, it looks something like this. Okay, so we could say, all right, so this is f prime. Extrema on f prime, then POI on f. Okay, two more. Oh, one more. We're going to skip this. Guys, you probably have heard me talk a few times about theorem identification. This problem is a theorem identification problem. However, you can do it without knowing the theorems that we still have to cover. So that's why I was okay to put it on there. Yeah, so I'm not going to go over it because it's going to take a lot of time. So let's just wait till I talk about the theorems. Now for this last one. Okay, so a lot of times you are asked about different types of approximations for integrals. So we have trapezoidal sums, right sums, left sums. The right sum and left sum are with rectangles. They're often called right Riemann sum or left Riemann sum. Okay, but anyway, let's see which of these will give over or under approximations for this graph. Okay, so like a trapezoidal sum, and I'll just do, I guess I'll do two subintervals because that's just easy. Okay, so I'm just going to do two subintervals. Okay, so for a trapezoidal sum, you take the base, or no, this would be the height of a trapezoid. Okay, so this is going to be the height of the first trapezoid. And then for one base, you go from the right end point up, and for the other base, you go from there up. And I go like this. Okay, and then same thing here. So this is an over approximation. Now let's do a right Riemann sum. So base of the rectangle up to the graph from the right end point, complete it. Base, up, completed. All right, so this is an under approximation. And then left sum, base from the left end point up to the graph, complete the rectangle. Base, left end point up to the graph, complete the rectangle. And then this one is an over one. Okay, guys, I'll talk to you later.